The evolution of the Tyrannosaurs is probably one of the better known stories in dinosaur evolution. However, new things can always be learned. One team of researchers just published their work on digitizing the skulls of the Tyrannosaurs, throwing them in virtual squeeze boxes, reconstructing their jaw muscles, and figuring out their bite forces in order to piece together an idea of how they evolved their jaws and noggins over time. The results may not shock you, but the data and the journey will. The first theropod dinosaurs, like Eodromius and Coelophysis, were what we might think of as generalist carnivores. They ate anything they could find, kill, and swallow or cut up into smaller pieces. Once the non-dinosaur rulers of the Triassic were snuffed out at the end of that period of time, the theropods were ecologically free to explore new options, resulting in more specialized megapredators like your allosaurs, tyrannosaurs, spinosaurs, and abelisaurs. In order to understand how these later predators mechanically worked, specialized techniques need to be employed. This is when paleontology gets help from the field of biomechanics, understanding how biological things mechanically work. With long extinct critters, computer models, math, and sometimes physical experiments have to be used, as opposed to the actual observation and testing of living systems. These biomechanical analyses have helped to broaden the understanding of many extinct animals, especially when it comes to assessing the feeding function and ecological role of the dinosaurs, and in this case, the theropod dinosaurs. A new study, published in the journal The Anatomical Record in September of 2023 by Evan Johnson Ransom, Feng Li, Xing Xu, paleoartists Raul Ramos, Ulrike Thorn, and Adam Midzuk. Wait a minute, the name sounds familiar. Oh, that's right, that's the fellow I work with to bring you all the Animal Planet's most extreme scale animation segments. It's Adam. The author team also consists of Kyle Atkins-Weltman and Eric Snively. This team applied comparative biomechanics to the evolution, ontogeny, and ecology of feeding in the Tyrannosauroidea. The term Tyrannosauroid may not specifically ring any bells, and this is because many of us are more familiar with the generalized and most often colloquially used term, Tyrannosaur. This can technically be used for any member of the Tyrannosauroidea, but I should make note that you can only call members of the Tyrannosauridae Tyrannosaurids. It doesn't really matter too much. The Tyrannosauroids were a group of highly specialized theropods more closely related to birds than most other hypercarnivorous predatory theropod dinosaurs, like the allosaurs, ceratosaurs, abelisaurs, spinosaurs, and megalosaurs. I think it should go without saying that this group is one of the most well-studied of not just theropod dinosaurs, but of all non-avian dinosaurs, thanks to its last and most prominent figurehead, Tyrannosaurus. Members of this huge group were characterized by their fused nose bones, teeth at the front of their jaws that were D-shaped in cross-section, and high levels of agility compared to other large theropods. Thanks to many new finds from the base of the Tyrannosauroid tree, the evolution of the group as a whole has become better known. These small, early critters like Guanlong, Dilong, and Moros have been hypothesized to be snippy little skittering generalist carnivores, similar to but still distinct from the very first theropod dinosaurs. They lived alongside and to some degree under the shadow of the much larger allosauroids. Once these groups began to decline in some northern hemisphere continents, the smaller early tyrannosauroids were able to take advantage and diverge into newer and larger forms throughout the Middle and Late Cretaceous. Thanks to the culture and well-earned popularity surrounding Tyrannosaurus rex, it has become the most studied extinct organism ever. As such, there are a bunch of studies on the feeding, bite force, finite element modeling, and feeding traces of the Tyrant lizard king. Features that allowed Tyrannosaurs to engage in powerful feeding functions include its expanded jaw and neck muscles, structural proportions of the skull, fused nasals, and a functionally solid skull. Other analyses have examined feeding function in other tyrannosaurs, such as Gorgosaurus and Tarbosaurus, but there have been fewer considerations of feeding function broadly across Tyrannosauroidea, including early tyrannosauroids such as Dilong, Guanlong, and Yutyrannus. The team set out to evaluate the feeding function in Tyrannosauroidea through muscle force reconstructions and finite element analysis. They also used Tyrannosaurus and Tarbosaurus skulls at different life stages to see how strong their skulls were as they aged. So, the team constructed 3 hypotheses to test. Hypothesis 1 states that tyrannosauroids can be broadly organized into gracile-snouted and robust-snouted based on their skull anatomy. Gracile-snouted tyrannosauroids possessed long and shallow snouts, with this snout region encompassing 70% of the skull. Robust-snouted tyrannosaurid skulls, on the other hand, were tall, broad, and with robust individual elements. They therefore expected these slender-snouted forms to be able to take greater physical stresses than the robust forms. Pretty simple here, but you still have to show your work and prove it. Hypothesis 2 posits that as Tyrannosauroid body size increased, the level of skull stress decreased, which fits with what would be expected. Larger structures can take higher forces than smaller ones. Hypothesis 3 says that, given the broad skulls of robust tyrannosaurids, the team suspects that juvenile tyrannosaurs of the broad-snouted forms would have stronger jaw muscle forces than tyrannosauroids of similar size. So, for this study, the team included Proceratosaurus, Dilong, Raptor-rex, early-stage juvenile Tarbosaurus, late-stage juvenile Tyrannosaurus, Teratophonius, Yutyrannus, Gorgosaurus, Daspletosaurus, adult Tarbosaurus, adult Tyrannosaurus, and an old adult Tyrannosaurus in their sample. With this sample, the team conducted a finite element analysis. I have brought this up every now and again, but it is good to refresh one's memory on exactly what this is. The finite element method, or FEM, is a popular method for numerically solving differential equations arising in engineering and mathematical modeling.
To solve a problem, the FEM subdivides a large system into smaller, simpler parts called finite elements. This is the solution, which has a finite number of points. The finite element method formulation of a boundary value problem finally results in a system of algebraic equations. The method approximates the unknown function over the boundary.
This is the most obnoxious thing I've ever experienced in my life.
So basically, FEM is used to predict/test the behavior/performance of the system in its service conditions virtually, with the help of computer programs. It is a numerical method which breaks down the system or object into a finite number of points called nodes. Governing equations or mathematical equations which describe the behavior of the system are solved at each of these nodes, and the solution is interpolated and represented all over the system. FEM helps tremendously in producing stiffness and strength visualizations and minimizing weight, materials, and costs, which is why it is often used in biological research and can then also lend itself to understanding how extinct organisms perform against different stresses. Watch this video by The Efficient Engineer to understand the process further. Anyway, the author team applied finite element analysis to 3D models of skulls of all of the tyrannosauroids in their sample. Ironically enough, the team were given permission to use the 3D skull models of Proceratosaurus and Dilong created by Raul Ramos for David Silva's Beast of the Mesozoic toy line. I had also gotten permission to 3D print those skulls to use as props, but still haven't gotten around to it. Small world though, huh? These skulls were based directly off of real fossil specimens and therefore approximate the true dimensions of the fossils quite accurately, though of course not 100% precisely. For example, the Proceratosaurus holotype is missing the crest and dorsal portion of its skull, resulting in the missing material composited from Guanlong, a close relative of Proceratosaurus. The adult and juvenile Tarbosaurus skulls and the Yutyrannus skull were sculpted by Adam Midzuk, our very own model maker, a very skilled individual who has also lent his skills to such creators as Tierzu and others. The same can also be applied to Gorgosaurus and Daspletosaurus, which were sculpted by paleoartist Ulrich Thon, who modeled the two tyrannosauroids from the holotype specimens. They also got CT scan data from Brian Cooley, Pratibha Bali, and Stephen Rowe for sculpting, scanning, and making a model of Sue the Tyrannosaurus. They got scanned surface models of Jane the Tyrannosaurus from Dr. Larry Whitmer, Heather Rockfield, and Ryan Ridgely. They got a scan of the Raptorex skull from Jeff Parker, a scan of Teratophonius from Gaston Design, and a scan of the nation's T.rex from the Smithsonian. All of these models were flawed in that they lacked all of the inside bits, like endocranial cavities, and all of the air pockets that allowed dinosaurs to get as large as they were. This underestimates stresses in some regions of the skulls. The stress results therefore serve as hypotheses subject to further testing and refinement, in order to make everything as similar as possible so that the stress tests weren't uneven across the different skulls. The team refined every scan or 3D model by smoothing out details and fusing all of the individual skull bones into one structure. Once all of the skulls were ready to go, the team needed muscles. The muscle forces of the Tyrannosaurs were estimated based on muscle reconstructions of archosaurs created by many previous researchers. Then they did some quick maths and measurements to get the general dimensions of the jaw muscles for future tests. So, what did they find? When comparing the jaw muscles and skull lengths of Tyrannosaurids as they age with that of similarly sized Tyrannosauroids, the juvenile Tyrannosaurines, Tarbosaurus and Raptorex had bigger jaw muscles than the small early Tyrannosauroids, Dilung and Proceratosaurus, which halfway disproved the null of Hypothesis 3. Among medium-sized Tyrannosauroids, the juvenile Tyrannosaurus has bigger jaw muscles than the similarly sized Teratophonius. Among large Tyrannosaurids, the adult Tyrannosaurus has much larger jaw muscles than other large Tyrannosauroids such as Daspletosaurus, Gorgosaurus, Tarbosaurus, and Eutyrannus. Adult Tyrannosaurus has wider and longer holes in the bottom of the skull, called subtemporal fenestrae, than in other Tyrannosauroids, meaning it had bigger, stronger muscles than its body size would suggest. For example, it has about 30% more than that estimated for a Daspletosaurus skull scaled to the same size, as this chart clearly shows. They basically proved most of their hypotheses, but better to be sure than to just assume. Wouldn't be science that way, right? Of course, Tyrannosaurus would be at the top of the heap here, with the smaller and thinner critters near the bottom. Let's move on to this graph, showing the estimated jaw muscle forces per critter. Juvenile Tyrannosaurus showed expectedly low jaw muscle forces compared with adults. Adult Tyrannosaurus such as Sue and the nation's T.rex were capable of exerting high total jaw muscle forces at 63,322 and 60,788 newtons respectively, allowing them to apply high tooth forces when biting. The paper states that other large, robust snouted tyrannosaurids showed total jaw muscle forces that were lower than that of an adult Tyrannosaurus. This included Tarbosaurus, Daspletosaurus, and Gorgosaurus having total jaw muscle forces of 11,905, 14,360, and 10,910 newtons respectively. The paper continues, adding that medium-sized Tyrannosaurians, such as Teratophonius, showed a total jaw muscle force of 5,232 newtons, with a correspondingly smaller jaw muscle force than a juvenile Tyrannosaurus. Early-stage juvenile Tyrannosaurians such as Raptorex with 1,156 newtons and a juvenile Tarbosaurus of 623 newtons showed high total jaw muscle forces than small early diverging Tyrannosauroids. For example, Proceratosaurus had 390 newtons and Dilung had 337 newtons. Both Raptorex and the juvenile Tarbosaurus had a wider range of jaw muscles than the smaller early Tyrannosauroids, suggesting that juvenile Tyrannosaurians had stronger bites, a trend that would continue as they aged. Eutyrannus had a total jaw muscle force of 2,405 newtons, which was lower than a juvenile Tyrannosaurus and other large, robust snouted Tyrannosaurids. The large Proceratosaurid possessed a skull length of 60 centimeters that was shorter than that of large, robust snouted Tyrannosaurids, but comparable to the skull length of a late-stage juvenile Tyrannosaurus. Now we must move on to the FEM analyses that determined structural strength in the skulls. Color coding was used to identify levels of stress, with red being an indicator for high stress and blue an indicator for low stress. They found that, as you can see, the level of stress is rather high in the juvenile condition of Tyrannosaurus, but decreases upon aging into the adult form. Both of the smaller juvenile Tyrannosaurines, T.rex and juvenile Tarbosaurus, exhibit high skull stress, although the level of stress magnitude is higher in the T.rex. Both the adult Tyrannosaurs and adult Tarbosaurs exhibit moderately low skull stress, although these stress concentrations occur at different locations of the skull. Although Tyrannosauroids exhibit varying levels of skull stress, stress concentrations occur at consistent areas of the skull such as the nasals, lacrimal, pterygoids, and quadrate. Small, early Tyrannosauroids and juvenile Tyrannosaurians show higher stress than the low values present in robust snouted Tyrannosauroids. From a layman's perspective, it seems as though D-Long has the weakest skull, with Proceratosaurus following. Eutyrannus has low stress distributions across the different parts of the skull, but had a lot of stress in the palate. The ornamented snout had low stress, similar to the crest of Proceratosaurus. Gorgosaurus has similar stresses to Teratophonius, with low stresses throughout the skull and with moderately low stress in the back of the skull and the palate. Gorgosaurus exhibits lower skull stresses than the similarly sized Daspletosaurus. Daspletosaurus has higher stresses than the similarly sized Gorgosaurus. Higher stresses are present throughout the skull, with higher stresses in the palate, nasals, nasal maxillary suture, and the palate. Next up, Teratophonius has got lower stresses than a similarly sized late-stage juvenile Tyrannosaurus. Lower stresses are mostly present in the front chunk of the skull, with moderately low stresses in the back and sides and low stresses in the palate and pterygoid bones. The juvenile Tarbosaurus, on the other hand, has got stresses in the same places as the adult Tarbosaurus, but with higher overall skull stresses than the adult. Moderately low stress in the front of the skull and relatively high stress is in the sides of the back of the skull and palate. The adult Tarbosaurus has generally lower stress than the others, with higher stresses in the palate and the back and the sides of the skull. Stresses are also found in the front of the skull, though not as strong as in earlier Tyrannosauroids. The T.rex has higher stresses in the back and sides of the skull and the palate. The juvenile Tyrannosaurus has lower stresses than T.rex, with low stresses in the front of the skull and some parts near the back. The highest points of stress are located in the back of the skull where most of the jaw muscles were, plus some stress is spread out over the middle of the skull. The adult Tyrannosaurus seems to be the most resistant to stress, with the highest stress located in the back where the muscles were, and just a little bit of it in the bridge of the snout where it transitions from nasal bones into the maxilla bones. The least amount of stress is in the center of the skull and the front. Finally, we have the elder Tyrannosaurus that seems to be less resistant to stress than the last skull. Higher stresses are located in the same areas, but there seems to be a more gradual spread of stress across the skull, with the least affected areas being the bottom of the maxilla bone, the eyebrow bone, and some parts of the back of the skull. So, with all of the data collected, what does it all mean? What did the author team interpret from this? Hypothesis 1, that the gracile-snouted Tyrannosauroids would have higher stress values than robust-snouted Tyrannosauroids, is supported. All of the analyses show this trend. Hypothesis 2, that skull stress would decrease with an increase in body size, did not consistently occur. The small critters like Proceratosaurus had low skull stress values in contrast to the higher stress values in Gorgosaurus and juvenile and adult Tyrannosaurus and Tarbosaurus. The results of many of the tests seem to contradict Hypothesis 2. Hypothesis 3, that juvenile Tyrannosaurians such as T.rex, juvenile Tarbosaurs, and juvenile Tyrannosaurs would have higher jaw muscle forces than similarly sized Tyrannosauroids such as D-Long, Proceratosaurus, and Teratophonius because of bigger spaces in the skull for muscles, is supported. Those juveniles did seem to have more muscles and stronger bites going on. What implications do these results have for the Tyrannosaurs as a whole? Well, it shows that the small tyrannosauroids had weaker skulls and bites, and that later tyrannosaurs had much stronger skulls and bites, with their juveniles having weaker skulls than the adults but much stronger bites than the similarly slender-snouted ancestral tyrannosaurs. This may indicate something with regard to how juveniles fit into the ecology of late Cretaceous Laurasian ecosystems, but this is definitely something for future analysis. What about those early tyrannosaurs? The early diverging Chinese pan-tyrannosaur, Dilong, had a weak skull and not a lot of jaw muscles, so probably not a super strong bite force compared to juvenile tyrannosaurines. They were probably going after smaller prey such as mammals, reptiles, and small bird-like theropods. Previous work on the inner ear and brain of Dilong found that they had good agility and balance but weren't great at smelling, at least not as great as their final descendants. Dilong did have fused nasal bones though, so it seemed they were adapting towards fusion of the skull for reducing stress when biting, even in this relatively diminutive form. Similarly to Dilong, the small Proceratosaurid, Proceratosaurus, has a weak skull. Proceratosaurs had teeth of similar shape to those in juveniles of later tyrannosaurids. They were flat from side to side and blade-like. It also had a slender skull and jaw, suggesting the animals were better at killing and eating smaller prey items. That big fan-like crest in Proceratosaurus showed some stresses in the FEM tests. The authors think this may mean the crest acted like a buttress against stresses on the skull when the animal bit down. This is a practical use in combination with the already hypothesized display purpose. Proceratosaurus also had fused nasal bones, like Dilong. The much bigger early tyrannosauroids, like the Proceratosaur Eutyrannus, had deeper skulls that ditched the flashy crests. The nasal bones in Eutyrannus were strong and had low stress values, possibly supporting the idea that the crests of Eutyrannus, which were along its snout and over its eyes, may have helped resist stresses against large prey items. Once we get to the true tyrannosaurids, we first stop at the more gracile Albertosaurines, represented in this study by Gorgosaurus. Work by other researchers has found that the Albertosaurines had what is called ontogenetic niche partitioning. This just means that they went after different kinds of prey items at different stages in their lives, helped by their anatomy drastically changing as they age. The young had quite slender snouts, blade-like teeth, and long skinny legs. Adults had beefier skulls, thick railroad spike teeth, and shorter muscular legs. Then we get to the end of the line for the tyrannosaurs, the Tyrannosaurines. Daspletosaurus took the more robust anatomy of adult Albertosaurines to the extreme, basically just being more robust and resistant to stresses and strains in the same but more exaggerated way. Daspletosaurus even lived alongside Gorgosaurus, something many researchers think was possible because the two predators were snagging different types of prey items, thus avoiding competition. The other Tyrannosaurine used in this study, Teratophonius, was an earlier diverging member. No feeding traces have ever been found that can be attributed to this animal, but it's presumed based on its general anatomy that it may have been going after hadrosaurs and ceratopsians in a similar though unique way to Tyrannosaurus and Gorgosaurus. Enough material is known to know that it went through different anatomical adaptations as it aged, with juveniles and adults going after different prey. Our second to last stop is the Mongolian Tarbosaurus, a tyrannosaur so similar to Tyrannosaurus that some researchers have argued to combine the two. However, Tarbosaurus as a whole was more gracile than Tyrannosaurus, and this was reflected in the tests run by the current research team. The change in ecological niche through life stages carries over for Tarbosaurus, with their young carrying slenderer, weaker skulls with weaker but still strong bites. And finally, we are at Tyrannosaurus. The work of this team show that Tyrannosaurus growth was dramatic, transitioning from small, generalized carnivores to large-bodied predators. Given their small and gracile skull, juvenile Tyrannosaurs were likely incapable of delivering bite forces as great as those of an adult Tyrannosaurus when scaled to the same size. They couldn't go after the mega herbivores they lived with. Wherever there were a lot of tyrannosaurs, the older juveniles became the medium-sized predators. They were more agile than an adult, and likely capable of hunting more gracile prey, such as ornithomimosaurs, pachycephalosaurs, thescelosaurs, and relatively smaller hadrosaurs and ceratopsians. They couldn't mash up bone like the adults, so perhaps their leftovers were taken by the adults. Given their size and reinforced skulls, adult tyrannosaurs were the biggest, baddest predators in their world. They had their pick as to what prey items they were mechanically equipped to handle. Nothing that was too small and swift though. They couldn't technically run after all. Their hardened skulls gave them an edge in crushing and smashing virtually anything they put in their mouths. Very efficient carcass carvers. Some may say, no duh, that this study shows what we already know. But I, and most likely the authors too, say that this sort of thing physically, or in this case virtually, and directly proves what could only be assumed. Instead of just going with a vibe, real science is done and specific parameters of stresses and strains and bite forces are determined. Their results show that tyrannosaurs really did just get beefier, stronger, and harder over time. Their juveniles became bigger and badder versions of their ancestors, while the adults grew into some of the strongest predators the planet has ever seen. One aspect that remains unknown, and something the team plans to study next, are the anomalous group of tyrannosaurs known as the Alioramines. This group is still enigmatic, with only 2 members, but represents an entire lineage of tyrannosaurs that closely resembled the slender juvenile forms of the later tyrannosaurs, but as adults. How did their skulls fare when thrown into the virtual squeeze box? Were their juveniles even more dainty, or were they a reverse Uno card and bulldozed their way through small but tough prey items? Only time will tell. Hell, why stop at tyrannosaurs? Throw the skulls of any prehistoric animal through this process. Who knows what information might be found? Well, Evan Johnson Ransom, the lead author, knows. Stay tuned to the Society of Vertebrate Paleontology 2023 meeting for some Spinosaur talks. Also, please follow the authors at their respective social media platforms to keep up with their latest and upcoming projects. Evan Johnson Ransom at EJR_paleo_MSC. Eric Snively and Kyle Atkins Weltman at OSU Vert Paleo. Raul Ramos at Raul Ramos Art. Ulrich Thon at Artsy Desplito. And Adam Midzuk at Kuzim_ZA. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, like this video, drop a comment in the comment section below, and hit the bell icon to stay in the know with everything Edge. Thanks for watching.